It was a great pleasure and honor, actually, to introduce Professor Panos Kevrekidis from University of Massachusetts, Amherst. So Panos was visiting us over the last 2.5 months now, and there was still opportunity to talk to him in the next 2 weeks or so. So I'll make it very brief. I think everyone is aware of Panos' achievements and contributions in the field of nonlinear waves. Particularly merging and combining theory, numerics, and experiments, which makes it quite unique. And on top of that, and as you can see from the title already, that he's working on different topics, on different waveguides, as we say, different media, which involve nonlinear wave propagation. And with that, I'll hand over to you, Panos. It was a great pleasure having you here. Thank you for coming to OIST, and I hope you enjoyed your time and will continue enjoying the next 2 weeks.
Thank you. Thank you, Amin. It's a great pleasure and opportunity to thank Amin for his invite to come to this program, to think about this program, to also thank Jonas and Lynn for making it much easier for me to be here and taking care of all the logistics. It's a great program, and I invite those of you that haven't exploited it to bring people here, please do. It's a wonderful program to have. I would love to have something like that in my own university. So a plug for the TSVP. Thank you all for coming. I will try to keep it. Mandate was to try to keep it for a broad audience. I will try to keep it to a broad audience. Let's see if everyone gets a little something that they might be interested in. We'll see how it goes. So I want to talk to you about joint work with a number of good friends and collaborators. As I say, whatever good you see in here should be attributed to them. Whatever bad should be blamed on me. This is mostly work with Dimitri Franciskakis from Athens, with a lot of numerical help from Ricardo Carretero and Jesus Cuevas. Some experiments, as Amin mentioned, I like to work with experimentalists, including very much so with Amin. So some experiments that I will show you from David Hall, Marcus Oberthaler, and J.K. Young. And there are too many to mention: postdocs, graduate students, and collaborators all around the globe. So a small tribute to them for all the help that they've given me to present this to you. So here's my introduction. I want to tell you a little bit about nonlinear waves. I will assume that you don't necessarily know about nonlinear waves, and I'll give you a bit of a sense of how they come from the real world to art, to science, and back to the real world. So try to give you a bit of a glimpse about that. Then I will try to tell you a bit about the history of the subject, starting from the early 1700s or 1800s, and then going all the way to Los Alamos, one of the places that is near and dear to my heart, and then coming all much closer to today, to a couple of Nobel Prize winning discoveries or inventions, if you will, associated with the lasers and Bose-Einstein condensates, and finally some recent twists related to origami, since we are, after all, in Japan, and also to pandemic waves, and finally conclude and give some future challenges. Now, as you may gauge from my name, I'm Greek, so I would be amiss not to mention that there was some reference to waves in ancient Greece. In particular, Pythagoras was interested in how the pitch of musical instruments relates to their length. But the waves that I am interested in and I want to tell you about today are much more related to Japan in some sense. They were the kinds of waves that Katsushika Hokusai kind of represented, this great wave, which is from the 36 views of Mount Fuji, which you can see kind of in the background. And this great wave is kind of a recurring theme in Hokusai's work. By the way, Hokusai is a pretty amazing figure. First of all, this work is parallel to the Mona Lisa. It's the most recognized Japanese work of art in the Western world. That's one sort of big credit to it. It's also, Hokusai is paralleled in some ways to Leonardo da Vinci in his impact in modern art and in Impressionists and all that. But the interesting thing about Hokusai was he's kind of quite a character. If you haven't read anything about him, I would very much invite you to do so. One of the sort of quotes or paraphrasing the quote that he said was, well, which is kind of, I don't know, heartwarming for someone like me. He said, well, anything that I did up to age 70, it doesn't matter. It has no significance. Then around age 73, I realized something about animals and plants. By age 86, I got deeper. By age 100, I will reach the marvelous. And by 110, my hand will be alive by itself and will be drawing things and so on. So he was quite a character. In his art, not only when it mattered, like when he was 70 and beyond, but also even when it didn't matter, when he was in his 40s, he was drawing these giant waves that today we call Rog waves or freak waves sometimes. This, by the way, is sort of some fast cargo boats, which, if I understand correctly, in Japanese are called oshiokuri, or were called oshiokuri back then. So he was drawing these in his 1805 drawings, and even earlier, around 1803, off of Honmoku, which, if I understand correctly, is close to Yokohama, or a port near Yokohama. He was drawing these kinds of boats and waves and so on that were sort of a preamble to his great wave kind of work. So you see these waves kind of recurring in the art of Hokusai, and these have sort of excited the minds of people and the imagination of people and the work of people in things like digital photography. But I don't want to focus on that. I want to focus a little bit on how this affects science. I don't know if that can be removed somehow. But anyway, so I'm going to tell you a little bit about how this affected science. So going from observation that affected Hokusai to art, and then from art going to science. And now let me see how I can play this. Oh, I couldn't play this here. Okay, that's not good, because I need to play my movies. Okay, so I will do it this way. So this is sort of an experiment that happened by Ton van der Bremer in the University of Oxford, a collaborator and friend, who kind of worked with some colleagues in Edinburgh to actually demonstrate something analogous to the great wave. So they were doing an experiment in which they were sending waves at a certain angle, water waves, as you see in a tank. The tank is in Edinburgh, and these waves interfere at a certain angle of 120 degrees. And as they interfere, you will see through the digital camera that something is captured, and the something is very much parallel to the great wave that Hokusai kind of observed. So notice the waves here, there is already some patterns that are forming. And as these patterns are forming, you will see that over time, they start forming something which very much parallels the great wave. So you will see them kind of side by side, and you will see that it parallels a bit the great wave that Hokusai was observing. So this is, let me go back to the slideshow. Okay, there we go. So that was, oops, hopefully it will come. Yeah, so that was sort of the work of Ton van der Bremer, reconstructing the great wave that Hokusai, so art influencing science. But I would be amiss not to mention that here at OIST, you have one of the world's leading groups in studying these kinds of giant waves. And this is from the work of Amin, who very kindly lent me some of these JPEGs. So you can see there is kind of this wave that is coming. This is all to scale in a sort of water tank, and is kind of ready to affect this boat. And the wave kind of arrives at the boat. The wave kind of crushes the boat and eventually tumbles the boat. So this is kind of the kinds of experiments that Amin is doing to scale to try to understand these kinds of effects and the impact of them in kind of ships and similar kind of constructions. So this is also a movie. Let's see if I can play this one. Yeah, this one I can play. This is also coming from Amin's work, or from Amin's presentations. So this is an offshore facility. So this is science, or real world affecting art, art affecting science, and science sort of going back to the real world. This is the sort of thing that inspires Amin and his group in terms of their studies. These are studies of these sort of large waves happening, and I will sort of fast forward so that we don't waste too much time, so that you see kind of the most important, perhaps, effect in this offshore facility. You can see this is an offshore facility that is used for drilling or other kinds of purposes. And you see this kind of giant waves, and the most giant one kind of happening now that is occurring in real time, sort of in this situation. So this is the kind of motivation for some of this work. And now I will sort of come to the details of what the work is about. So the kinds of waves that I want to tell you about are not quite like these waves. So when you think about waves, you might think of a sinusoidal wave or something like that. So a wave with a given frequency or a given wavelength or something like that. In fact, if you roam the OIST gallery somehow and you see all those screens, they all sort of seem to have these nearly sinusoidal waves, which actually are not quite sinusoidal because they start spiking. And I'll talk about that in a little bit. But I'm not interested in those kinds of waves today, those kinds of periodic waves. Rather, I am interested in waves that have these robust characteristics that seem to have sort of a characteristic length scale associated with them, waves that are actually localized. This is what I mostly want to talk to you about today. And these waves, I want to really give you two messages, such that when you forget everything else about this talk, these are the two main messages that I want you to remember. The first one is there are two fundamental mechanisms. One is dispersion, the other is nonlinearity, that conspire to create these waves. I will explain each one of the mechanisms and how they conspire. But this is the first main message that I want to give you. And the second main message is these waves are ubiquitous in the world around us. If you remember these two things when you forget everything else about this talk, I will be a happy person. All right, dispersion and nonlinearity. What is dispersion? What is nonlinearity? And now those of you that are physicists or mathematicians will know what dispersion is, but I'm going to try to explain it for the rest of you. If you have a wave packet, a sort of localized entity, which is like wave-like, it may consist of multiple frequencies and multiple wavelengths that are kind of lumped together. But these frequencies and wavelengths may travel at different speeds. And as they travel at different speeds, they may spread out and may sort of break apart your structure, your wave packet. So this kind of breaking apart, this dissolution, if you will, of this wave packet is due to dispersion. So this is what dispersion does. It kind of breaks things apart. It sort of dissolves them. On the contrary, nonlinearity does completely the opposite. This is also coming from your experience. If you go to Tancha Beach and you look at the waves, what will you see? You will see that the waves kind of start steepening and eventually they break. What does this practically mean? It means that larger amplitudes move faster than smaller amplitudes. It's a nonlinear effect. So the waves kind of tend to localize. So nonlinearity, contrary to dispersion, is the thing that tends to localize waves. So we have one mechanism that tends to spread things apart. We have another mechanism that tends to lump things together to sort of focus them, as we say. The combination, the competition, the interplay between, the balance between these mechanisms is the thing that creates the waves that I want to talk about. Okay, so these are these localized solitary waves that, and keep this in mind, that propagate without changing structure, without changing shape, without changing form, without changing speed. Their character is preserved as I go and travel through. These waves kind of stay robust, propagate with a constant speed, propagate with a constant shape, do not alter over time. So this is the kind of waves that I have in mind that come, as I said, based on my first tenet on the interplay between dispersion and nonlinearity. And in fact, even when you have multiple ones of them, they will still be very robust. So here's the tall and thin and fast interacting with the short and fat and slow. And you see they interact like particles. They kind of almost do not feel each other at all. And even if you have three of them, the tall, the middle, and the short, they may sort of change their character in the middle, but they still propagate unscathed, unchanged, because they are robust due to this interplay between dispersion and nonlinearity. So these are the waves that I'm going to be talking to you about. And these waves do appear in the setup. I will try to keep the math to a minimum. I kind of promised that. But I do have to have some math at least. So these waves appear in shallow water waves, which is the kind of place where you would expect waves to appear. And in these shallow water waves, what you measure is the change or the rate of change, the time derivative is the rate of change of the height of the wave. So this depends on space and time. And this comes from two different mechanisms. That third derivative in space is the dispersion thing, is the thing that tends to spread things apart. And that nonlinear term, nonlinear because it's quadratic, it's like u squared derivative, that is the focusing term, that is the localizing thing, that is the thing that tends to break the waves as they go. So the interplay between dispersion, the second term, and nonlinearity, the third term, produces this robust, localized structures that we see in these equations. Okay, and these equations appear in different forms, and they still have these kinds of waves. So here I have a couple of other examples, including one which is Schrödinger-like and will recur later in the talk, revolving around quantum mechanics and so on, but I will come back to all of that, okay? All right, so this is the first tenet, dispersion, nonlinearity, interplay, creating these waves. Now I want to convince you that these waves are universal. They are kind of in all the world around us, or in many places in the world around us, not only in optics, atomic physics, and water waves, but also in elastic systems, magnetic systems, in biological systems, in sort of atmospheric systems, and even planetary systems. So I want to give you different scales and different paradigms, because the second thing that I want to take out of this talk is about the different places where these waves appear. Okay, so here are a couple of examples. The first example is biological in nature and has to do with ourselves, with a human, okay? And it has to do with a blood pressure wave, something that we all experience. In fact, we measure every every so often. And now that they get older, more often than not, unfortunately. But anyway, so these blood pressure waves are because the heart sends a pressure wave through the arteries, right? And we measure that kind of pressure wave, essentially. And that pressure wave turns out to be described by the same kind of equation as I showed you for water waves. How is that? Well, let's make some assumptions, which are not excellent assumptions, but are sort of somewhat reasonable assumptions. For instance, let's assume that blood is a constant density, no friction fluid. Again, not a perfect assumption, but a reasonable assumption. Let's assume that the artery is a long circular cylinder, and then the waves along the artery are being transported by blood. Essentially, the cross-sectional waves of the artery are being transported by blood. This is what the first equation says. The second equation says something about the evolution of blood as a fluid. And the third equation is a constitutive equation that says if the artery has a cross-section, that induces pressure, okay? If you put together mathematically these three ingredients and you analyze them through appropriate mathematical machinery, then you will end up with exactly the same equation as I showed you before. That is, the pressure, the time evolution of the pressure has dispersion and nonlinearity. The combination of the two produces blood pressure waves, exactly the blood pressure waves that we measure in a human organism. And you may say, okay, big deal. So what's important about that? Well, what is useful about that is that by knowing this, you can actually convert things that you know from medical practice or biological practice into mathematical quantifications. In particular, for instance, you know smoking is bad for you, right? So this is something that has been demonstrated and so on. The question is, how do you show that mathematically? Well, mathematically, what happens when you smoke is that the arteries become more rigid. What this means is that the Young's modulus, an elastic parameter in the system, increases. When the Young's modulus increases, what this means for this blood pressure wave is that the amplitude of this wave and the speed of this wave increase. So you get larger pulses that move faster through your system. And that for your system is bad, okay? So that's how you quantify how smoking affects sort of the increased arterial pressure. In addition, you know that fat accumulation is bad for you. I certainly can attest to that. That is because the thickness of the arterial walls increases, and when the thickness of the arterial wall increases, then the amplitude of this pulse, as well as the width of this pulse, also increase. So you get larger pulses, wider pulses, and again, this is bad for your organism. So you get a mathematical quantification, mathematical translation of things that you know from medical practice into these waves, into these arterial pressure waves through these kinds of mechanisms. So this is an example at the human scale of these kinds of waves appearing. So this is my first example. My second example is a magnificent, a glorious effect that I'm sure you haven't heard about, which is called morning glory. This is an effect in every spring in the Gulf of Carpentaria in northern Australia, where there are these amazing waves. This is now not on the human scale, this is on the scale of our environment. These waves are about 1,000 kilometers wide, they're about a couple of kilometers high, and they travel between the towns of Burketown and Normanton in northern Australia. And of course, they travel they travel very fast as they go above the sea, or they sort of slow down and decay when they go above the land. And sometimes you see just one of them, sometimes you see many of them. And air transports material to these waves on the one side, on the front side, and turbulence sinks the air on the back side, but they travel unscathed, unchanged in shape or form over kilometers, over many, many kilometers, so many that they can actually be observed from an airplane. So here is a bunch of these waves that are being observed from an airplane. You can see the wing of the airplane over there, and you can see the waves kind of forming and emerging in this hundreds of kilometers or thousands of kilometers kind of scale. So this is a scale not of the human, but the scale of our Earth environment, right? Scale of hundreds or thousands of kilometers. Here's a scale of planets, okay? This is something that you also know from your experience or from your astrophysics or hearing about it, the giant red spot of Jupiter. This is an anticyclonic storm that is being preserved between the northern and the southern jet. It's something which is sort of anticyclonic. It's a vortex-like pattern, and this vortex-like pattern has a size of about 28 kilometers long and 14 kilometers wide. That's about twice the size of our Earth. So I talked to you about the human scale. I talked to you about 1,000-kilometer scale. Here's something on the scale of our Earth that is being preserved in over 350 years and counting, Okay, and in fact, as I was preparing this talk, I realized that one of the interesting astrophysical questions is how long will this survive and how fast does it decay? But it almost does not decay. It decays very little and will be there for a long time. And the Voyager mission kind of observed this thing as it was approaching Jupiter and was sort of monitored in 1979, this anticyclonic storm. And now we have much better observations than those. But this is something that happens not on a human scale, not on the environment scale, but on a planetary scale about these waves. So remember, the two things that I want you to keep when you forget everything else is the interplay of dispersion and nonlinearity creates those guys, and these guys exist everywhere around us, okay? So this is my two main messages. Now I want to take you through some anecdotes. I want to sort of take you a little bit through the history of this subject, the history of nonlinear waves. And the history arguably starts with this gentleman, an amazing person, Leonhard Euler, who actually wrote about 900 papers, amazingly enough, some of them, or many of them, the last 20 years of his life when he was blind. And he actually put together the equations for frictionless fluids, which are the equations that are quite important for what we are studying. Then, through an intermediate figure, L'Hopital, this passed on to the French classics. Those of you that know sort of physics or mathematics will know the Laplacian or the Laplace equation or Laplace transform. So Monsieur Laplace over there, as well as Lagrange of Lagrange multiplier fame or Euler-Lagrange equation fame. The French classics tackled these water wave equations. But it was not until Professor Cauchy kind of came into the game that these equations got some of their initial solutions. So it turns out this was such an important problem in early 19th century that for maritime economy, for commerce, for science, and so on, that the French Academy of Sciences put together a prize for the solution of the equations of the water waves. And Cauchy was the one that actually got the prize because he used the work of another exceptional gentleman, Joseph Fourier, of Fourier analysis or Fourier theory or harmonic analysis fame, which had just been developed at the time to actually solve the problem of the linear wave equations. Remember, we're interested in nonlinear phenomena. This was just the solution of the linear wave problem. By the way, as a small interesting anecdote, Professor Poisson of Poisson's equation fame was both a judge in this competition that Cauchy won, but he also submitted the paper in the competition itself. So maybe interesting times. But nonetheless, let's move to the next step, because as I told you, I want to talk about nonlinear waves. So the next important step happens across the English Channel. So I now move you to the UK and to the 1840s. And this is probably one of the most interesting figures that you may have never heard about. His name is John Scott Russell, a Scottish naval engineer, who is a pretty amazing figure. If you look him up, you will see that he was involved in things like measuring the Doppler effect. He actually did sort of one of the first experimental realizations of the Doppler effect. He was involved in mechanical carriages, the preamble to modern cars. He was a Scottish naval engineer, so he designed hulls of ships like the Great Eastern, which was the biggest ship of its time. But the thing that he's really most well known about is the wave of translation. In particular, the British Association for Advancement of Science, similarly to the French Academy of Sciences, realized the importance of waves. And what they did is they set up a committee on waves, of which one of the two members was Scott Russell. So this committee produced reports about what waves are about. And Scott Russell had this amazing epiphany, which is in his own words over here. Remember about the waves that I told you about, right? These are waves that move without change of shape, without change of form, without change of speed. Let's hear Mr. Scott Russell. He says, I was moving on horseback, and then there was a vessel. Of course, he was an engineer, naval engineer. He was observing vessels, and the vessel stopped. And as the vessel stopped, there is this large, solitary elevation of water, a rounded, smooth, and well-defined heap of water that continues its course along the channel without change of form, without diminution of speed. So this is exactly the first time that such a solitary elevation, such a solitary wave is being reported. He says, I followed it on horseback and overtook it still rolling at a rate of about 8 to 9 miles an hour, preserving its original figure, about a foot to 1.5 feet in height, until much later, about a couple of miles later, I actually lost it in the windings of the channel. Such was, at the August of 1934, my first chance encounter with that singular and beautiful phenomenon, the emergence of these nonlinear waves. So this is the first reporting, or in literature, if you will, in this report of the Committee on Waves of this solitary wave structure. In fact, the guy got so engrossed, so into this thing that he was an engineer. He kind of, in his backyard, he created water tanks, and he tried to reproduce what he was seeing. So he actually sort of immersed some weight, and he was creating elevation. These are his drawings, by the way, from 1840-something. And he sort of tried to reproduce what he saw. About 150 years later, a colleague from Edinburgh, from Heriot-Watt University, Chris Eilbeck, tried to reproduce his drawings. And not only that, he got really into this, and in fact created a conference. He organized a conference at Heriot-Watt. And by the way, some of my collaborators are in that boat, which actually tried to reproduce exactly what Scott Russell saw. So what they did is they had the boat, they stopped the boat abruptly, and you see that elevation, that heap of water that marches forward. They created a solitary wave analogous to what Scott Russell had seen. And if we now march forward to much more modern times, here is, in a modern version from Christophe Finot, a version of this in a water tank with a fluid that is colored so that you see what it is. And you can see this elevation of water that is traveling unscathed, that is sort of not changing in shape, not changing in form, not changing in speed, just traveling, getting all the way to the end of this tank, and then sort of reflecting back. And so it still continues to propagate without any change in its shape. Okay, so these are the kinds of solitary waves that we are talking about in this context. But as I told you, I would like to sprinkle some controversy, some anecdotes in the story. So here is an anecdote about this story. It turns out Scott Russell presented this to the mathematicians of the time, and he got sort of rebuffed. Basically, the mathematicians said no, including the guy that was actually the person that had written literally the book on sound vibrations and waves in musical instruments. Sir George Airy said, no, this is all kind of linear waves. It's sort of, simple stuff. And then Scott Russell kind of really got enraged with this, and he kind of said, well, you guys, you know the equations of fluid motion. You should be able to predict what I saw. This is like a real thing. And in fact, with just a touch of cynicism, he said, well, after this has been done, it now remains for the mathematician to predict the discovery after it had already happened. Okay, so he was kind of mocking the mathematicians of his time. So that created stirred quite a controversy at the time, and in fact stirred quite a controversy for a couple of decades. In these couple of decades, important things happened, but the controversy was not resolved. Here's one of the sets of the important things that happened. This very stern-looking professor, or Sir George Stokes, made some truly fundamental developments, including something about the periodic waves in water. That's not what he's most well known for. What he's most well known for was because with Claude-Louis Navier, a French mathematician, they discovered, or they brought forth, the most fundamental set of equations for fluid mechanics that we know to this day, the Navier-Stokes equations, that have been since then and for a couple of centuries the subject of fascinations of physicists, mathematicians, and engineers alike. Perhaps mathematicians more than everyone else, because there's $1 million prize to show whether these equations, that is water, blows up. Now you'd say, you must be crazy. Water blowing up, that means water forming a finite time singularity at the level of these equations. That, if you prove in 3 dimensions, you get $1 million. So it's that important. Anyway, that's not the main thing in my story, so I will not talk about the Navier-Stokes equations. I will continue on to my controversy. It took until about 1871. Remember, Scott Russell, 1844. Now we are at 1871 for this controversy to be resolved. And interestingly, it got resolved in Scott Russell's favor. That is, we go back through the channel, we go to France, and this is Professor Joseph Boussinesq over here that wrote down the equations for shallow water propagation in a channel, and he triumphantly for Scott Russell discovered that there is this kind of wave that travels unchanged in shape, unchanged in speed, unchanged in form, propagates through this set of equations. But then I kind of jokingly say, you may observe Professor Boussinesq, he looks really sad. And I usually say, jokingly, this is my interpretation, if you will, he looks really sad for at least two very important reasons. The first very important reason is you may or may not know that there were about 72 scientists, mathematicians, physicists, chemists, and so on, the most important of their time in France, that were engraved in the most important work of construction at the time in France, which was the Eiffel Tower. So 72 names appear in the Eiffel Tower. So all the important figures that I mentioned before, Laplace, Legendre, Lagrange, the mathematicians Cauchy, Poisson, Fourier, the physicists Coulomb, Ambert, Fresnel, the chemists Le Chatelier, Lavoisier, Gay-Lussac, they are all in the tower. Not so unfortunate Professor Joseph Boussinesq, who was kind of left out because he was considered very young. It's kind of unfortunate. There were even more unfortunate things that happened, and because OIST, I think, values diversity, I want to mention one of them, which is that there is not one female mathematician, physicist, or engineer that is engraved in the Eiffel Tower. I think that's a grave omission, especially because Sophie Germain, whose work was very important for the actual structural stability of the Eiffel Tower, her work on elasticity, she is definitely not there. So anyway, that's hopefully many things have changed since then. But let me mention the second reason why I usually interpret that Professor Boussinesq is unhappy. And that's another anecdote which says that sometimes scientific discoveries do not quite get credited where they should. And so although Professor Boussinesq was the one that discovered those equations, it was not to him that the equations, or his name, that the equations bear. Rather, they bear the name of two Dutch mathematicians that rediscovered the equations about 25 years later, mentioned the work of Boussinesq, did, to their credit, they did some important discoveries like the periodic waves of the equation, not the solitary wave that we talked about. And that's perhaps why Professor Korteweg, with his student De Vries, rediscovered the equations, has a smirk in his face, perhaps. The equation got the name of Korteweg and De Vries, and ever since has been called the Korteweg-De Vries equation. So that's what I will call it ever henceforth. And that's kind of the end of my story with Professor Boussinesq. Here is the actual wave, just one last time, dispersion, battling, and balancing nonlinearity, creating these waves of elevation, nonlinearity and dispersion balancing out for the rate of change of the elevation, and the wave is parameterized by a single parameter characterizing its amplitude, its inverse width, and its speed. That is the wave of this Korteweg-De Vries equation. Now we know what this is. All right, and here is an example of that. Here is kind of a risky surfer along this kind of almost one-dimensional wave. If you might go sort of to Moon Beach or Tiger Beach or Tancha, you might see one of these waves. This is my favorite kind of environment to mention that. But these waves also appear in completely different scales. This is the Strait of Gibraltar, which is about 13 kilometers wide, about 300 meters deep. And there are waves of density. And you may see these internal waves of density. Now they're kind of nearly radio waves. And the Challenger mission in 1984 kind of imaged these waves for the first time. But they do not exist only in this one-dimensional form or this quasi-one-dimensional form. Waves exist even in these kinds of two-dimensional forms, in this kind of X-like shape. And I want to mention this because there are some works like the one by Professor Mark Ablovitz, who is one of the sort of most famous figures in this topic, with his student Doug Baldwin. They actually imaged on their own with amateur photography these kinds of waves. So you see these two-dimensional waves forming these X's, and you see now a Y wave sort of perhaps forming over there, these X waves again, and so on. And these are from a delightful little paper. Let me not show you the entire thing. It's from a delightful little paper about a dozen years ago. And what they saw there is they saw these kinds of, first of all, I should say, these waves are now two-dimensional, so they're not described by the KdV, but by a variant of the KdV that involves the second dimension. And that equation was discovered by two Soviet scientists, Kadomtsev and Petviashvili. And this KdV has these waves that look like X's, has these waves that look like Y's, has these waves that look like Z's, almost like an alphabet of waves, if you will. And the X's, for instance, can have a short stem as in the top. They can have sort of an intermediate stem as here, or a long stem as here. And then Ablovitz and Baldwin, in their amateur photography, they were able to observe every single one of these kinds of patterns. So these patterns are not just a mathematical construct, it's something that appeared in these kinds of beach waves in shallow water. Okay, so this is, I think, quite an interesting thing. So this is now I have kind of finished the part of my history until 1895, right, which was Korteweg and de Vries. Now I did a little jump to the modern times. Let's keep that for a little bit. I'm at 1895. And you might ask, what was the next step? Well, sometimes in science, the steps take a long time. It turns out for the first half of the 20th century, nearly nothing happened in this field, okay, which is very surprising, but perhaps not very surprising if you know about the work of Henri Poincaré. But let me not get into that. Let me tell you about the next chapter in this thing, which comes in a completely different place, in a completely different time. We're now around 1955. And we go to post-World War II Los Alamos after the Manhattan Project. There is an amazing range of physicists, mathematicians, and engineers that are in that place and no longer need to work on weapons. They are now working on sort of what they know best, which is science, okay? And so one of them was Enrico Fermi, a Nobel Prize winning physicist. And Fermi had a sort of very fundamental controversy in his mind. I will try to do it some justice. In linear systems, we know like a string, we know a string has modes. It has sort of a fundamental mode. It has a first excited mode, it has a second excited mode, and so on. A string has modes. But if you have a linear system, it turns out these modes each do their thing. They never cross-talk to each other. Okay? They do not interact. On the other hand, Fermi knew that thermodynamics, the world around us, equilibrium thermodynamics predicts that these modes should each have the same energy. That is, they have to interact, exchange energy, and come to an equilibrium, which is equipartition of energy. And then he said, there is no way, I cannot reconcile these two things. And he had this brilliant idea that said, the only way that I can reconcile this is by including nonlinearity. The linear system cannot do it. Nonlinearity has to contribute. And so he worked with his friend Stan Ulam to formulate a nonlinear model that might have this equipartition. The problem with that is, you know, linear systems can be solved kind of mathematically, analytically, more often than not. Nonlinear systems, more often than not, cannot be solved analytically. So what would we do today that we know about computers and so on? We would throw this in a computer and see what it spits out, right? Well, this was 1955, and computational science does not exist, right? Los Alamos was the first place where such a thing as computational science is being born. And one of the people that is involved in that is John Pasta. So they bring John Pasta on board, and they are planning to use this machine to actually do the first scientific computation, if you will, of the time. And now you may, I mean, the machines that you have in mind are sort of your iMacs and your iPods and iPads and laptops and so on, these compact, elegant machines. Back then, the machine would take an entire room and would make these amazing noises. And the machine would be affectionately called Maniac 1. By the way, Maniac stands for Mathematical Analyzer, Numerical Integrator, and Computer. Okay, so Maniac 1 is who they tasked to actually solve this problem computation. This was one of the first computational experiments of the time. But before I tell you about the experiment and what it showed, let me mention about the person at the end, Mary Tingu. Well, nowadays, if you try to program something, you will open your Windows and in Julia, in Python, in MATLAB, wherever, you will start typing your code. Back then, that was not possible. You had to give it to a programmer that would actually write it in a sort of punch card and put it in the computer for it to be executed. And I don't know if you have seen the movie Hidden Figures. If you have seen it, you will know what I'm talking about. If not, let me just say that at the time, there were people that were called human computers to whom you would give the task of creating the code, running the code, getting the output, plotting the output. And that was Mary Tingu, a graduate of the University of Wisconsin, that did all that work. And now, before I actually tell you about FPU or the Fermi-Pasta-Ulam problem, let me talk about a very interesting anecdote of diversity, equity, and inclusion of that time. So here is the work of these people, which, by the way, was never published in a paper. This is very bizarre by itself, but there are two explanations for that. One is the results that they got kind of contradicted Fermi's initial intuition that nonlinearity would cause equipartition. So maybe that's why they didn't publish it. The other reason, which is the more practical reason why they didn't publish it, is that Fermi actually died an untimely death because of radioactivity in 1954. However, to the benefit of the nonlinear science community, when you work in Los Alamos, you have to actually write technical reports on what you do. And so they actually had to write a technical report on their work. And here is the most famous technical report of all time from Los Alamos, LA 1940, with a pretty arrogant, I would say, by today's standards, titled Studies of Nonlinear Problems, okay, which actually, and here's the highlighting is mine, has the following very interesting feature. It says the report was written by Fermi, Pasta, and Ulam, but the actual work was performed by Fermi, Pasta, Ulam, and Chingu. And so that meant that ever after this got known as the Fermi-Pasta-Ulam problem for the next 50 years, and the paradox that I will tell you about that's associated with it was called Fermi-Pasta-Ulam paradox, and Chingu appeared nowhere, okay? Until about 50 years later, there is this wonderful article that Thierry Dozois wrote and said, well, now in 2007, when Fermi is gone by 1954, Ulam is gone in 1984, Pasta is gone from 1981, Mary Chingu is still alive and kicking. And she was the one that actually did all the work that is shown in that report. And by the way, Mary Chingu is still with us at 97. This is a picture that Thierry very nicely shared with me from 2024. And Dozois concludes, it is finally time for us to give a proper recognition of Mary Chingu's contribution. Let us refer to this henceforth as the Fermi-Pasta-Ulam-Chingu problem, okay? So some things are changing over time, hopefully, and I hope they will get even better as we go along. But okay, anecdotes aside, let me go back to the science. And the science says, Mr. Robert Hooke told all the physicists since time immemorial that linear springs have an equation, Newton's equation, mass times acceleration is the restoring force from the two springs on the left and right. These are linear springs that we know and love and know how to solve. However, Fermi's genius was to endow the system with nonlinearity, to introduce additional nonlinear terms that he thought, believed might induce this equipartition. However, they didn't. So they actually put the energy in one mode, and they saw that it started to distribute in other modes, but then the energy came back. It did not equipartition. It did not distribute to all the modes on the strings. And that was sort of a bummer. But it was a bummer that was explained, at least partially, a number of years later, around 1965, because Ulam gave talks about the Fermi-Pasta-Ulam-Chingu problem, and a brilliant mathematician called Martin Kraskell sort of caught wind of these talks and sort of learned about this. And he himself gave a talk at Princeton in 1965, and a brilliant also computational scientist called Norm Zabasky was in the audience, and the two of them got talking, and they said, oh, we can do something about this. And the something that they could do about this was kind of the following. You have these springs, and they are kind of quite discrete. But if you sort of distance yourself from them, they can kind of look like a continuum. For those of you more physically or mathematically inclined, you can do a Taylor expansion and go to a continuum version of this problem. And the continuum version of this problem was the same equation that Professor Boussinesq had discovered in 1871. And if you analyze it, you end up with the same equation that Boussinesq, Korteweg, and De Vries had found in the 1800s. So 60 years later, or almost 70, in a completely different setting, the Korteweg-De Vries equation reappears. Before it was in water waves, now it is in nonlinear oscillators. And why is this important for Fermi's conundrum? It is important because this equation has dispersion and nonlinearity. As such, it has solitary waves, the kind of solitary waves that Zabosky and Kraskell found. And what did we say about solitary waves? They trap the energy forever. They do not exchange. They do not change shape. And therefore, they would not allow equipartition. They would take the energy, trap it for a long while, and not allow equipartition, explaining the paradox of Fermi-Pasta-Ulam and Chingu. By the way, this is an open problem to this day, whether equipartition does happen, because this equation is only valid at some intermediate scales. And it turns out that Professor Fermi was actually probably right in that at very long time scales, the problem does equipartition. But that's a different talk in and of itself. Here, I want to highlight that this Korteweg-De Vries equation reappears 60, 70 years later in a completely different setting, okay? And now, having said that, I will come to more modern realizations, although I will start with something that happened around the same time, or got awarded the Nobel Prize around the same time. And this is the laser. And the laser was awarded the Nobel Prize in physics in 1964 to Charlie Towns and two Soviet scientists, Basov and Prokhorov. And here is just a cartoon by Julien Bobrov about what the lasing is about, for those of you that don't know about this. So quantum mechanical atoms can be in a ground state. This is very simplistic, but they can be in a ground state or they can be excited, like myself, perhaps. And then a photon can come and hit them. And as it comes and hit them, there is a phenomenon called stimulated emission by which the atoms fell back into the ground state and more photons were produced. So if you now have a solid state matrix of many of these excited atoms, like Bobrov put over here, and you throw photons at them, they produce more photons, de-exciting the atoms. And as they produce more and more of these photons in a coherent state, these photons form a coherent beam, which we can actually harness through this as the laser beam that is so important for more or less many of the things that we do to this day, from laser pointers that I'm not using today, all the way to LASIK operations that correct our vision and all that. But this is important for me because this kind of light propagation is something that we use that uses exactly the same ingredients as I mentioned. So if you have optical communication in silica glass, the optical fibers that you kind of know and love because they make your internet very fast, this optical communication has, again, dispersion. It has the effect of spreading things out. Light propagation should be spread out. But this media, like silica glass, also bear nonlinearity. There's something called the Kerr effect, which says the refractive index of this media is nonlinearly dependent on the intensity of light. And this interplay of dispersion and nonlinearity creates robust pulses, 0 to 1 pulses. So the 1 is pulses and 0 is no pulses, that can be used for optical communications. And these optical communications are not a fictional thing or a thing of the lab. It's a thing that already in the early 2000s was used in sort of transmission lines. So transmission lines working with solitons, transmitting optical information over 3,000 kilometers in Australia from Perth to Adelaide already 25 years ago. So this is something that can really be used for practical commercial applications in principle. So these are my bright solitons, these sort of bumps that are sort of on top of a vanishing background. But it turns out there is also another breed of solitons that I want to talk about, which are kind of in connection to our dark side. So they have light on the left, light on the right, and sort of a dark dip in the middle. And for that reason, these solitary waves are called dark solitons. So they are localized, but it's a localized dip as opposed to a localized bump. And the reason why I mentioned this is because it's connected to another Nobel Prize winning discovery, which has to do with what is called Bose-Einstein condensation. Now, what is this? Well, it turns out that Bose and Einstein in 1920s discovered that if you take your favorite alkali atom, like rubidium or sodium or lithium or potassium, and cool it to the lowest temperatures known to man, the lowest temperatures of our universe, nanokelvin temperatures, something quantum mechanical and phenomenal will happen. The atoms will go from the excited states of the system, all of them or a macroscopic fraction of them, to the ground state. They will form a superatom, and that superatom is deemed or is called the Bose-Einstein condensate. Now, why is this interesting? Well, it's interesting for many reasons, including that it used Nobel Prize winning discoveries like laser cooling to be realized, but it was deemed so important in the physics community that only 6 years after it was realized, the 3 experimental wizards that were able to reach these very low temperatures, these nanokelvin, this coolest in the universe temperatures in their labs, they were awarded the Nobel Prize in physics. And what I want to show you is why this again involves dispersion and nonlinearity. Remember, I talked about the human scale, I talked about the environment scale, I talked about the planetary scale. Now I'm going to the micro scale, micrometers and milliseconds, and that's where Professor Erwin Schrödinger rules the land. This is quantum mechanics. And you know quantum mechanics, or if you have heard about quantum mechanics, you know that things satisfy this kind of Schrödinger's equation, which has this kind of second derivative term. That's again my dispersion. It's the thing that spreads things apart. But what spices life up is that the atoms interact with each other, and that produces nonlinearity. So again, although these are confined atoms, so they have some potential, the interplay of dispersion and nonlinearity produces localized structures. And since I want to always make some OIST connections, I made one with Amin. I want to also make one with Thomas Bush. It turns out that in these systems, there are not these bright solitons that I showed before, but rather these dark solitons. You see, there are atoms on the left which are white, atoms on the right which are white, and a dip in the middle. That is the one localized structure. It turns out Thomas Bush was the first person that characterized the motion, the Hookean-like motion of these dark solitons inside these Bose-Einstein condensates. He was the one that wrote down the evolution equation of these things. So again, they have sort of an OIST fragrance, these kinds of solitary waves. What we did is we studied how multiple ones of them kind of oscillate and interact, how they remain robust under interactions. And people like Markus Oberthaler reproduced this in their experiments. They saw how multiple solitary waves oscillate and interact in these kinds of traps. So this is from an experiment of a few years ago. And this is all in sort of one-dimensional systems, but higher dimensional systems are interesting too. And you might think, what is interesting in higher dimensional fluids, right? There is this toy that I often find in German playgrounds where you sort of rotate the fluid, and as you rotate it faster and faster, you will see this vortical structure that forms in there. And so vortices are the canonical thing that happens in fluids, and similarly in superfluids. So I have this friend, David Hall, who actually does experiments. He sort of rotates the bucket with the superfluid, and he produces potentially two vortices. Or if he rotates more vigorously, he produces triangles of vortices. If he rotates even more vigorously, he produces quadrilaterals of vortices, and so on. I usually like to say, for those of you that are older like myself, there was a thing at one time that was called the rotary phone. The younger one among you may have never seen it. And in the rotary phone, you had to kind of dial the number. So I usually jokingly say that David kind of dials the number of vortices. If you want 1, he can dial 1. If you want 9, he can dial 9, and so on and so forth. So it's like a rotary phone for vortices in 2 dimensions. And by the way, you can even go to 3 dimensions, and you can have beautiful patterns, sort of hypnotic patterns, if you will, in 3 dimensions, like vortex lines, the one that I mentioned about the playground, or these vortex rings. And if you've never seen smoke rings that leapfrog through each other, I invite you to go to YouTube and search a video like that. These are like those smoke rings. These are leapfrogging vortex rings in 3-dimensional condensates of this sort. And they can really be materialized in the lab. And by the way, I always like to make this connection. Remember, from observation comes art, from art comes science, from science comes reality, and so on. So all of these are strongly interconnected. This is Van Gogh's Starry Night, right, which has lots of vortices that people have even analyzed, and you would be shocked to find that the luminance of this is kind of is strongly connected to Kolmogorov's -5/3 spectrum for turbulence. So they are in some sense realistic for turbulence, but no matter, they kind of reflect a reality, which is, by the way, in juxtaposition with a peaceful village, a turbulent reality of a world around us that is mirrored in a lot of the science that we do. So this is, I think I will skip this one, although Pythagoras would be making a reappearance. If someone asks me, I will play this movie, but I will go to, in the interest of time, I will go to my last 2 examples. One that is quite interesting to me. Oops, I do want to bring that up, but it doesn't want to be brought up. So I will sort of go out and do it like this. So this is origami, okay? And this is, remember I said 1895, Korteweg and de Vries, 1955, Fermi Pasta Olamtsingu. Now it goes 60 years later than that, okay? And I'm going to show you origami that actually looks like the Fermi Pasta Olamtsingu solitary waves. And this is a movie that the National Science Foundation put together and featured some of our work. And here's the work that was done experimentally by J.K. Yang and his group at Washington. This is what is called triangular cylindrical origami that is being manufactured in the lab. And then they manufacture a whole bunch of this origami. So you now create what is called the mechanical metamaterial. And this is a lattice of this origami. And what you do is you kick that lattice from one end, you create a wave of compression, and this wave of compression becomes a wave of decompression through this origami. You will see that it becomes predominantly blue. So it becomes a wave which is called the rarefaction wave or a decompression wave. And that is absorbing the shock of the impact. So this is something that people like to use, including these experimental groups, about impact mitigation and shock absorption and all these kinds of things. So 1955, 60 years later, just like 60 years before, of course, there was all sorts of things that happened in between. But 60 years later, in origami, which is a form of art used in science, the Fermi Pasta Olamtsingu problem recurs, which to me is kind of fascinating. Let me go back to my slides and show you the last thing that I want to show you, which is, hopefully it will come, which is dynamics of waves of infection. Just to show you yet another very recent example. When the pandemic broke out, we thought one of the things that we would like to understand is how these hotspots of pandemic infections kind of spread through the land, okay, how they spatially distribute. And we kind of, some of us were from Greece and some were from Andalusia in Spain in the team. So we used Greece as an example, though I usually jokingly like to say this is a much less interesting Greece because it doesn't have the islands. Nonetheless, we used Greece and Andalusia as examples of models of infection. In these models, we had susceptible individuals that would interact with either asymptomatic individuals that were very important for COVID because they went about their own business as if they had no infection, and also pre-symptomatic and infected individuals, and these would infect the susceptibles, would make them exposed, they would produce some copies of the virus, and then they would either become asymptomatic and then recover, or they would become infected after an incubation time and either recover or get hospitalized, or in a lot of cases there were fatalities. We know there were millions of fatalities coming from COVID. So we used a model like this in space and time to capture the number of infections in Greece and Andalusia. And just to give you an example, as we became more and more sophisticated in these models, we used these kinds of meta-population models that use different compartments. And I even sort of became quite familiar with the geography of Andalusia. This is Almeria, Jaén, Granada, Córdoba, Málaga, Sevilla, Cádiz, and Huelva. And we basically took a compartment for each, and we counted for or accounted for the mobility of individuals from area to area through cell phone data, and built a model that accounted for cell phone data mobility and how the infections would transfer from area to area. In the top is the model with this mobility, that is with people moving around. In the middle, there's the model without mobility. In the bottom is the actual data of observation. And what we observed was, unless you accounted for mobility, you would never really capture the proper patterns of infection, of transmission of infection in the actual system, in the actual physical locale of Andalusia, including in the total deaths or fatalities, but also in the spatial distribution of these fatalities and the spatial distribution of these infections. So this is kind of a recent paradigm of how this can be developed. And we actually even did mathematical modeling of these kinds of systems by taking simple examples. Like, for instance, you have a lattice of individuals, kind of like the lattice of Fermi Pasta Olamentsingu, and these individuals may move to nearby places, may sort of infect or get infected in these nearby places, and then they would go home. And then based on that, you would build a discrete model, and then you would do what Zabasky and Kraskell did and find a continuum model approximation to that, and then you would study these approximations and get information about the propagation of these infections. So what I'm trying to tell you is some of these ideas are pervasive in other fields as well. So let me just stop here and tell you what I just told you. Really, the two basic messages that I want to transfer, and that I would be very happy if you remember, is in these systems, there is two key ingredients, dispersion and nonlinearity. These two key ingredients are generic. As such, they create this generic interplay. As such, they create these generic waves. These waves transfer, translate, without change of shape, without change of form, without change of speed. They are very robust. These waves do not just happen in the lab. They happen inside of you as pressure waves. They happen around you as the morning glory. They happen in the giant red spot. They happen in the land of Mr. Erwin Schrödinger. They are ubiquitous and universal in the world around us. But not only do they exist in these sort of classical things like waterways, but even sort of atomic physics or nonlinear optics of laser propagation or optical telecommunications. They also appear in sort of less usual places. They appear in origami inspired metamaterials. This is kind of a novel direction. They appear in waves of pandemic infection, not quite in the same way, but in the same kind of spirit. They appear in the arteries that I did show you. They appear in waves of sort of transmission of disease in the brain that I didn't show you, and so on and so forth. So these waves are generic. They, as I usually like to say, joking a little bit, is that the range of these applications, kind of inspired by a paper that I wrote with my brother, has been inspiration for much of this work, kind of extends to infinity and perhaps a bit beyond. And with that, I would just say, if any one of you has any thoughts or interests or ideas or comments about this, I'm at the TSVP for 2 more weeks. I would be delighted to hear from you and see you and talk about science. Thank you very much for your attention. Thank you.
Thank you very much, Panos. This is very exciting and interesting talk. Of course, I'm aware of a few aspects of it, but I was not sure about the blood pressure, and actually I was checking yesterday. So
okay, good.
Do it more often than
I
you
can
think.
tell. Yes, I can tell you more about it.
Okay, so we have time for questions.
I think in the microphone. Yeah.
Thank you for the very nice talk. I have a question about the work you show with the dark solitons.
Let me go back to that.
It's actually maybe a naive question, or this one. Here, the conclusion says that dark solitons can be generated and collide elastically in atomic VECs. But at the beginning, you told us a lot that, look, these solitons pass each other. They don't interact with each other. So what's happening here?
Good. Well, even in the beginning, actually, the waves, if you sort of pay very close attention, they kind of transfigure. That is, what happens with the 2 and the 3 is kind of the one that is coming behind kind of assumes the role of the one that is in front, and the one that is in front kind of assumes the role of the one that is behind. So if you look at it from afar, it will look to you as if there is, it will look to you sort of, there are 2 things like this, and then there are 2 things like that. So it will look to you as if this guy is this guy, and this guy is that guy. But in reality, what happens is they kind of exchange their character in a sense, and there is still one that is traveling with a larger speed, and there is still one that is traveling with a smaller speed. So similarly here, these 2 kind of interact in a repulsive way, and so they still will have one that is kind of moving ahead with the speed that was coming in, and the other that is lagging behind with the speed of the other, but they are kind of repulsively kind of interacting. And the way that the repulsion kind of takes place, or the way that you see this repulsion, is that there is kind of a phase shift, which is, this is kind of more of a technical detail. There's kind of slight shift of the trajectory of the one and the other that kind of tells us about this interaction. I don't know if that kind of covers what you...
Yeah, okay. But how can you differentiate one from the other, actually?
Okay, experimentally it is super hard. Theoretically, there are ways to understand it by looking at what happens in the vicinity of the interaction. So in the vicinity of the interaction, you can see if these guys have trajectories that look like avoided crossings, that kind of is much more reminiscent of repulsion, or that kind of looks like approaching each other, meaning that as you have sort of a potential well, and as you approach the potential well, you feel the depth of the well and you get sucked in. So then you understand that this is involving attraction. So you can tell this way, and if you can have your mathematical toolbox, you can actually analyze this and find the potential of interaction between the waves, which is actually what we did here. What we constructed is an effective potential of the interaction in these waves, and what we put in that potential, just to sort of reiterate the work of Thomas Busch had told us that each one of these waves is feeling a parabolic Hookean potential, just as if it was by itself. But then we figured out by doing analysis that there is this kind of repulsive potential of interaction between the 2. So the effective potential that they feel encloses this attractive or restoring force that Thomas Busch had discovered with this repulsive force that we developed, and the 2 together gave us the effective picture of what is happening in the physical dynamics. Yeah. Yeah. Yeah.
Is this on? Now it's on.
Now it's on.
Now it's on. Okay, so I'm wondering about, so in the normal regular linear wave equation, right?
Yep.
You also have, like, if you just set up like an initial, disturbance, it will also create like things that propagate away from each other, right?
Absolutely.
So like, how do we categorize and differentiate between just normal linear, like translating things, and soliton stuff?
Okay, excellent question. I will connect it to the previous question. If you have 2 linear waves, this is exactly what you said. There is this so-called D'Alembert solution of the linear wave equation that tells us that we start with a disturbance. That disturbance will actually break into 2 disturbances, and these 2 disturbances will kind of split and go their own way. By the way, this in and of itself is something fundamentally different than what I told you about dispersion and nonlinearity, because in the nonlinear regime, what I kind of told you is this thing has the right shape, no matter what you do, you cannot break it into two ingredients that will actually go left and right. It will actually stay there and stay there forever, okay? So that is one key difference. But let's not take that. Let's take the example that you wanted, which is let's have these two things and kind of interact with each other. How can I tell that this is a linear or a nonlinear interaction? If they just go through each other, they will just follow trajectories as if they didn't see each other. They will just follow their own individual trajectories. If they do interact, as a result of this interaction, they may preserve their speed, but they will have a slight change in the position of their trajectory with respect to how they were coming. If I can draw this, the trajectory, instead of being like this and like that, it will be like this, but it will afterwards kind of be shifted by a little bit, and this guy will be shifted by a little bit. So they will have the same speed, but they will have what is called the phase shift that will tell you that these guys, they did feel each other. They did understand that they were being affected by another wave. And that is the effect of nonlinearity. In linearity, you do not interact. You do not perceive of the other person. You interfere with it, but you do not feel it really. Here, the feeling is very slight in some cases. Other cases can be more significant, but even in the most canonical cases, like the KDV, it is very slight, but there is an effect, and that effect is measurable, is accountable in the mathematical theory, and you can really diversify between the nonlinear and the linear in that sense. Okay.
Thank you.
Okay. Thank you very much. It was very interesting. So I got curious because you showed us a multitude of localized phenomena.
Yes.
That, if I got it correctly, you call solitary waves. Now, I'm from fluid mechanics.
Yes.
And typically, out of personal experience, when you argue, that's a wave, at least in some schools, you get hammered because to be able to argue that you have a wave, you need to prove that it's a solution to a specific set of equations or something like that, right?
Yeah.
While in your approach, it looked more like you see an isolated phenomenon, and then, you explore whether that is represented by some equations that you already have, or that, or you build a new model to describe it.
Yes. Yes.
So I think my question in truth is, what gives this phenomena that you have shown us the dignity of being a wave? So on which ground you can call it wave?
Yeah, that's a somewhat philosophical question, and it's a very, very interesting one, I will admit. So in all the settings that I did, indeed, I kind of followed the paradigm that you mentioned, which is I started from a physical setup, and then as I sort of formulated that physical setup, I tried to translate that setup into a modeling setup. And in that modeling setup, I looked for these fundamental ingredients. And once I had these fundamental ingredients, even if I sort of use paradigms from fluid mechanics of dimensional analysis and sort of balance of interactions, you can sort of find that there is a characteristic scale of something forming like a wave. So by even sort of something like this, you can guess that there is a wave present. But then you have to use mathematical machinery to establish the presence of this wave. And so what I then did, or in fact I more like alluded to, just because of the breadth of the audience, is I basically alluded to the fact that there are some universal equations in which, or to which, I can sort of convert my original system towards. And these equations are this nonlinear Schrödinger equation, this Korteweg-de Vries equation, or other equations like the Sine-Gordon equation, and so on. And when I get to these equations, I can get the dignity of the exact solutions of these paradigms, somehow these canonical nonlinear paradigms that have these exact solitary waves and so on. Then, going back to your question again, I have to make the argument that for experimentally relevant times, or for the times associated with my expansion that derive these equations, these phenomena, these nonlinear waves, are present in a laboratory or present in physical observation or something like that. But in as much as I can make this approach rigorous, meaning I sort of make some rigorous assumptions that sort of neglect some mechanism but keep some fundamental mechanism. Then I develop a mathematical model that encloses mechanisms, like Fermi-Pasta-Olamtsingu did. And then I sort of convert this through, say, multiple scale expansion or some other mathematical machinery into one of these equations. And then I know the time scales and the length scales and the amplitude scales of this approximation. And then within those scales, I can justify that this equation is valid, including in experiments. Then I come full cycle to saying these equations give me within the spatial and temporal scales an appropriate mathematical description of this physical phenomenon. And as such, they give me some information about the waves of this system. That information may not be forever. In fact, in the Fermi-Pasta-Ulam-Tsinghua argument case, I argued that this happens at some intermediate scales, but doesn't happen forever. So you may not be able to say, as if you were solving the Navier-Stokes or the Euler or something, that these are true waves that are persistent forever, but you are able to justify and explain something that alludes to physical observation and connects to experimental features. So I don't know, because philosophical, I know one can take different perspectives, but I hope I kind of address partially.
Any further questions? Okay, one more. One last one.
Thanks for the talk. So you also mentioned the Fermi-Pasta-Ulam-Tsinghua paradox, and if you want to see, like you said, if it actually goes to equipetition, then do you have to run it for longer, or like add extra terms, or like sort of extra physics that we are ignoring at this level?
You have to run it for longer is the very short answer. And the last time I heard someone that was, people are still doing it. And here's kind of, okay, this is maybe a little bit more for the experts, but here's the current version of it. The current version says, if you have significant more energy than Fermi-Pasta-Ulam-Tsinghua were unlucky enough to put in their initial conditions, if you have more energy, then you can observe with modern day computers that there is equipartition. You can see the equipartition happening. It turns out in the example that they did, they had so low energy that it will take so long times to actually see this, that the last talk that I heard said that if you use the best GPUs that you have running for 3 years in a row without any power disruptions, you might be able to tell that this gets to the timescales for which equipartition is predicted. So they were unlucky enough to hit such a soft spot where equipartition would take kind of practically forever to be realized. And so the short answer to your question is you really need to run long enough. Not to take more terms, because the original model, in this case, it was not kind of like the previous question where we were modeling something. It was a model that was postulated. Fermi said, let this be created, let this model be studied. And so this is the ground truth of this system. But you need to run this system for long enough to actually observe this. And the long enough here turns out to be dramatically long. So long that even to this day, some 70 years later, this has not been realized definitively in computations, despite the amazing progress that we've had in scientific computation. That's pretty remarkable in and of itself.
Okay, yeah. Okay, thank you very much, Panos, again, for a very inspiring presentation and also discussion here. It's great having you here at OIST. We hope to see you again also very soon. Thank you very much. Thank you for coming.
Thank you. Thank you all for coming.